you. Thank you very much, Fernando, for the nice introduction. Hello, everybody, and welcome to this lecture. So my name is Peter Lund, and I will speak during the next an hour or so about increased flexibility to improve integration of large-scale renewable energy schemes in the power system. And I talk with a brief insight on the market take-up of technologies. You will see here on the screen also some of the background material which I will employ. So if anybody is interested to get a copy of this, so just please send me an email and I'll send you the papers. Now let's start with the big picture and about the implications from the forthcoming energy transition. And see the implications in particular to the energy system and also to better understand the scale of problem of flexibility. I picked here two examples, two macro scenarios. On the left-hand side, we have a scenario by the shell, which extends till the end of the century. And on the right-hand side, we have an IA scenario up till 2050. So according to the IA scenario, renewables and energy efficiency together, I would call these technologies new energy technologies. They represent about 70% of the required measures to get the emissions down to a sustainable level. And we see that there's really a focus here on new technologies, innovations, which imply that the future problems cannot be solved with today's or yesterday's technologies. Now the left-hand scenario by Shell company, which extends till the end of the century, renewables would stand for 80% of primary energy, and with the variable renewable electricity like solar and wind, they would be close of half of all energy. Now, a clear implication from both scenarios is the increasing role of electricity, even beyond the traditional electricity demand, which in turn implies an increased demand for flexibility, and importantly, also cross-sectoral use of electricity. That is, electricity will flow to other sectors as well, such as transport or buildings, or even to industrial chemicals. Now let's just briefly review the implications of what these kind of scenarios have. And it's clear that such a big change in the energy system doesn't come without energy system changing. I've just depicted here a very simple example of how solar power photovoltaics would affect the load profile. The blue line here is the load for a typical day without solar, and the red line here would be a typical residual load with very much solar. Some may view this as a technical issue, so definitely type of duck curve that you see here that would require more and increased ramping capabilities of the remaining system, but this would definitely also have other implications, economic implications and political implications. So if the load profile change in this way means that during the noon time, price of electricity on the spot market dive, maybe go to zero and negative, and again in the evening time it would raise. And this would also be a major challenge for the remaining energy system, as many of the power plants cannot operate in this way. So there's some political implications. You may know that in Europe we speak about capacity market, that there should be some subsidies for traditional power to run those in order to match the new profile that we see here. That's why the question of flexibility is very, very important, in the sense that it really extends from technologies to economics, to policy making, and so understanding what we can do with flexibility for sure has a very many-sided implication. But let's briefly look on the relation of energy efficiency and renewables. In the big macro scenarios that we saw, the Shell scenario for the IEA, it seems to be separated by the separate entities, but as we move closer to the real energy grid, to cities, to buildings, you understand that the renewables and energy efficiency are much more linked together. So most of the energy, definitely, or all of the energy, is consumed in the end use side, and that's where we see the tighter relation of renewables and energy efficiency. I think this would be important, in particular in the case of urban areas, where, like cities, where about 2/3 of all energy is consumed now. In the future, even more so because of the urbanization. By 2040, 80% of all energy will be used in the built environment and in the urban environment. Now, the benefits of energy efficiency, in particular in the urban context, for large-scale renewable energy, renewable electricity schemes, that those are quite evident. First of all, if we use less energy, indeed, the less we will need energy supply. So that means that we would have less renewable energy. And the absolute need for flexibility would be reduced. Energy efficiency is very often also linked to demand-side management, which helps very much renewable electricity supply, please match with the power demand, and also gives a tool to better optimize the value and use of renewable electricity. And finally, of course, when we are close to the end use and speak about energy efficiency, that would also help with the sectorial reintegration, so integrating electricity over the different sectors in order to improve flexibility. So that's clear benefits from energy efficiency. There's for sure a range of flexibility measures that we can use of, and here I just picked a few examples of references which are quite interesting. Just gives you an overview of what we can use here. The flexibility measures range from very traditional ones of improving the transmission line or using spatial integration to smart grids. So then there's more sophisticated measures like energy storage, and of course we have energy efficiency, DSM, as one option. So the range of options available is quite large. Looking closer on the flexibility options, we find that typically energy efficiency would represent the most cost-effective ways to improve flexibility, like demand response would be one of those, or using ICT in different forms. But the magnitude of flexibility, the potential, though, would be slightly restricted. So this is very cheap, but the potential would not be large. So that's why we would need something else in addition, which brings us for sure to some more expensive solutions. In practice, when we speak about large-scale integration of renewable electricity, we would rely on a range of different flexibility measures. We'd have a kind of a portfolio to rely on, and in that sense, that would lead to a more sophisticated optimization to find the best mix. Now, a new interesting flexibility measure that's coming up, and you see it's growing pretty much in many countries, is the conversion of the surplus renewable electricity into other final energy forms. And here we note that that new kind of option as advanced conversion, shown here as a box, between the final energy forms and the energy demand. So the advanced conversion, or call it also power to X, X describing power to something. X could be heat, cold, mobility, gas, hydrogen, you name it. So that's where in particular the electricity would flow to the different final energy forms to the different demand sectors. So this kind of conversion of electricity enables us to meet the supply, the demand side better. So the electricity would not just go to the electric demand, but could also meet the other demands of final energy in this end use end. And in this way, we would be able to increase the flexibility of the power system, and that leads again to much better integration of renewable electricity in large scale. The key idea with power to X, but this kind of a power to something measures, is actually curtailment, cutting of renewable electricity oversupply. And by doing this kind of curtailment, what we actually do is we increase the supply side flexibility. The power to X would ease the renewable supply side should be more flexible. So basically, a curtailment would be kind of a shaving the supply in the same way as demand side shaves demand. So this is a quite simple approach. In terms of cost, would be I would say comparable to DSM on the demand side. The curtailed power can be used further, and again, in referring to the previous slide, you could use it for heating, transport, or you may just leave it there. So the simplest way is not just to curtail and then do nothing, but again, if you curtail much, that's kind of a extra supply of electricity would be worthwhile to use in other sectors. Curtailment would enable major oversizing of the renewable electric system beyond the self-use limit. Now, on the left-hand side, you see a picture where we just illustrate the oversupply. The line 546 is the self-use limit of power, and if the renewable power like 1, 2, 3, see that. So in cases you would not be able to transport that electricity beyond the city or beyond your house, you would need to curtail the triangle 2, 5, 6. So that would be the extra power which you need to do something with. One advantage with the oversizing would be, though, here is that if you oversize from the traditional maximum self-use power limit, which is the 1,463, you see that the oversized renewable system 1,563 would produce even more power below the self-use power. So by oversizing, we would definitely get more power even below the self-use limit. So 154 plus 463, those triangles is the extra that we get below the self-use limit itself. Now, what's the point of oversizing? Yes, you could produce more, actually, renewable electricity even when the weather is bad. And if the weather is too good, then the question is that you may need to curtail and think about what to do with the curtailed power. There's a major benefit in the inherent nature of renewable energy for curtailment, because the capacity factor of renewable electric systems is much below 100%. Typically, the capacity factor of solar power is around 10%, maybe very good conditions 15, 20%. And for wind, we have capacity factors around 30–35%. Now, so if I curtail the power, so I limit the power of wind or solar below what it could produce, the energy loss would be very simple. It's the capacity factor times curtailment times the time I curtail, as you see here. So let me give you an example. If I had a very large wind power scheme, and I would curtail the power for 30% for 1 month in a row, meaning that if I normally would have let's say I would have 100% power, and I curtail it to 70%, so I would operate the whole system below what it could produce. I would, in this example, with 30% curtailment and 1 month curtailing in a row, which is a very long time, I would actually lose just 1%, so less than 1% of the wind energy produced in a year. So it means that for shorter times, let's say 1 month, 2 months, you could have a quite kind of dramatic curtailment, and it wouldn't actually lose so much in the energy. So, so power cutting or the energy loss is not directly proportional in this case to the power cutting. But there's also another benefit with curtailment. So let's say that we are operating now our wind power or solar power system below the power level that it could produce. Let's say that we would be here at 0.2 and we curtail to 0.4. So the power difference between 4 and 2, so that's in a way in a reserve. And it means that actually we could, by curtailing, running the power plant at lower than it could be level, we could provide very fast primary reserve for the power system. So now solar and wind would have this kind of reserve power features, which may be very beneficial. You can ramp up the power plant back to 100% very quickly. There's a solar in a few milliseconds. There's a wind in a few seconds. So that gives you a very kind of new kind of ramping up, and of course ramping down is always easy, but ramping up kind of properties which has a clear value. So it means that the very sporadic solar and wind would have anyway some reserve power features which could be quite beneficial. Now, if you just curtail very little, the energy loss is not that much. So maybe you don't care about the curtail power. But if you start to curtail more, then it's of course a question about that, what to do with the surplus power that we have. Now, in my presentation, I try to keep the renewable electricity within the city or within the house, so we try to avoid it flowing beyond the boundaries. Of course, if you have a very good grid, you could sell the electricity to neighboring cities or to the electric market. Now let's try to keep the kind of surplus within our frame. If doing nothing is the easiest way, so that, let's say the second easiest way to handle with the curtailed power would be to make actually thermal energy out of electricity. So making heat or chilled water. That's what we typically need very much of in the cities and in our buildings. Or you could even store that heat or store that chilled water for later use. In case of power to heat, where we use electricity for heating, the easiest way is just to use electric resistance heat. That's very, very cheap. Now, adding a heat pump, you could even boost the heat production. And from 1 unit of electricity, you get 3 units of heat. So in that sense, you could kind of use the overflow of electricity also to supply larger amounts of thermal energy in the building side. let's take a more closer look on the power to heat scheme. And as I'm coming from a cold climate, we need a lot of heating. But those colleagues from the southern climates, I would say the same analogy here would work also for cooling. And indeed, even though I'm using my home city, Helsinki, here as an example, in my presentation, we've also done analysis for countries like China, Shanghai, India, city of Delhi, Chile, the city of Concepcion, and in Saudi Arabia, the city of Tehran. And one could say that the conclusions that you will see here in a while would be very much the same. Independent party in south or in north, but we need always building thermal energy, bring that heat or chilled water. Now the rationale for the power to heat, which is more relevant for, let's say, colder climates like Europe and US, Northern Europe, it's important to recognize that most of the final energy that we need in cities would be thermal energy, or in this case, heat. For instance, in Helsinki, my hometown, 2/3, over 60% of the final energy is actually heat. So by viewing the power and heat system integrated, the thermal side could actually function as a buffer to large-scale renewable electricity variation. So we could kind of easily oversize now the renewable electricity side, and the surplus that would be taken by the thermal side. What is also very important to recognize that the storing thermal energy, being cold water or hot water, is relatively easy. It's an established technology. And it's much cheaper than batteries, typically 1 order or even 2 orders cheaper than a lithium-ion battery. And you can apply thermal storage in very large scale. So the scale and the economics for using thermal storage store in a way too much wind or too much solar, which you would indeed use anyway for, let's say, air conditioning or heating. That would be a good option indeed. Let me now then show a few examples of simulation results to demonstrate benefits of large-scale renewable electricity schemes, and also oversizing renewable electricity beyond this Celsius limit that very often will be set as a limit. And I would apply here curtailment, and I would also utilize different flexibility measures, in particular the power to heat schemes, but also DSM to some degree. And we use Helsinki here as an example. You see here on the top the city and the profile of electricity use. That's the blue, and a profile of the heating demand. And the small dots here, that would be kind of heating plants, boilers, and the yellow spots here on the left-hand side would be the major power plants. I don't think you use very much district heating and combined heat and power, but most of the combined heat power is based on coal and natural gas. So definitely there is a major interest to try to reduce the CO2 emissions and also, in that sense, look on different electricity and renewable electricity options. Now, the results that I show here are hypothetical, and what I will do here basically is to introduce more and more wind in this case, and let's see how the energy system would cope with that, and how the different flexibility measures would help us. So the first case is the one where I just look on wind energy production on a yearly scale, hour by hour, and the worst date for wind energy happens in Helsinki around early February. This is a measured case where there's a very big gust of wind in, and would be a case for overproduction. The first case numbered here as 1, and we see here here the gray line is the average electricity demand. You see here that limiting ourselves to the power demand only, and avoiding to exceed that limit. So we would keep ourselves under the self-use limit. We get a wind profile here, which on a yearly scale would produce about 20 to 25% of the electricity in the city. Limiting ourselves to the self-use limit, which may be actually quite practical, because if you have a lot of wind power, if the storm, most likely the price of electricity in the exchange would go to 0, and selling electricity outside the city is the base case. Now, if I look on the heating and electricity as a whole, that brings me to the upper curve here. This is the heat plus electricity together, and the gray bars here are the heating. That would increase my wind output. I could increase it to the curve 2. So what I do here is now I take the wind and the power demand and heat demand as the limit for wind power, and I use power to heat conversion to convert the difference between 2 and 1 into heat. So in this sense, by using the heating system as a buffer, I could actually increase the amount of wind energy. And now, let me point out, this is hypothetical. I would could increase it by a factor to 2 to 3 without solar wind power being overflowing beyond the city boundaries. So in this case, wind power, as now when there's a wind still, we could still produce some wind power. On the yearly level, wind could actually stand for about 60% of the electricity in the city. Now, the share of wind-based heat of all heat would be just 2%. So it just shows that we don't need to curtail so much over the year. And if I added a heat pump here, then the share of wind heat of all heat may come up to around 5-6%. But oversizing and curtailing may be quite effective, actually, to increase the amount of variable renewables. Let me go further and increase the sophistication of the simulation and analysis by adding demand-side management and storage, but also considering solar and wind. So let's see how those match together. And then I would also look on control of the flexibility mechanism. So when I have, let's say, many flexibility mechanisms, the control of these may be more important. In the previous case, we just look on this load and supply matching, but I added here also a link to the real electric market. So we're looking on the price, on the spot price of electricity on the electric market, and trying to optimize against that price as well. So we use the flexibility measures in a market condition case. So let's see first on the result on the power profile as an input to the simulation. So let me just open up slightly the numbers of the power profile. Here we see the power profile of Helsinki over a year on an hourly scale. You see the daily cycle and the season cycle. But there's also interesting data which may relate to energy efficiency, and that's the shiftable loads. We have measurements of major kind of demand, and being able to locate different shiftable loads. So and extrapolating those then to a full scale, city scale. You see here a range of shiftable loads, which on a hourly basis represent from about 10 to 50% of the power demand. So this is our kind of analysis that, yes, you have the shiftable loads, but they vary very much from power to hour. The shifting time that we assume typically for the shiftable loads would be 1 hour. But we see that some of the loads here, the load components could go up even to 8 hours, but typically we use now here a slightly shorter demand-side management options. The first result relates to the surplus of variable renewable energy production. So we have now wind and we have solar. So let's see what kind of a surplus we have here. In the region where, so we have both PV and wind, and the axes here, we just have one of the technologies. So the x-axis here, on this axis we have just PV, and on the y-axis we have just wind, and in the plane we would have a combination of both technologies. Now there's a region here where when the sizing of the PV and wind is modest, you see there would not be very much surplus in the cities. So most of the power here would be surged by the city itself without any flexibility measures. Had we just photovoltaics, so when we start to increase it, you see that the surplus of the photovoltaics will increase. So this curve here would show the surplus of the photovoltaics, which we need to deal with. And in particular with solar, where the supply peak comes around noon. That's where demand side management could actually play a role. In the Helsinki case, we see that the demand side management could reduce the surplus by about 5 percentage units. It means from 20%, about a quarter could be saved with DSM. So with photovoltaic and DSM, there's a very good combination. Whereas if we go for wind energy, just pure wind energy, which matches better with the winter load, that's where we see that the demand side management would give you a smaller benefit, which can maybe 2-3%. Introducing power to heat, that gives a major kind of benefit, so that we can kind of cut the surplus of wind or solar. So if I would introduce the power to heat, that means up 35% units reduction in the surplus. So the surplus is with the wind, maximum would be like 40, 45. I could bring the surplus below 10%. So now looking on the heating or thermal and power system together, I could kind of reduce the surplus quite significantly. There's also different options for power to heat here. We look on using storage, district heating, accumulation, so accumulate heat in the district heating network. These kind of benefits are marginal. They would be maybe 3 to 6% units, in this, let's say, comparable to demand side management. But the big kind of change is really is the power to heat conversion that we. Now, we also looked on the economics, and if I just draw a few lines here, I've got a few conclusions on the economic side, and what we do here is basically looking on the, in this case, on the cash flow from flexibility. So our measures are linked to the electricity market, and let's see how the cash flow would be influenced by flexibility. First of all, the base case here, we denote it with 100%, and that's where we don't have any flexibility. So if you see that here, that if you look at 1 and 2, in base case, all flexibility measures, demand side management, power to heat, storage, you name it, they would bring you a benefit in terms of cash flows. So you get really a better economics when we look on flexibility. So here I'm optimizing against the spot price of electricity, and you see that with DSM I could get about 10% better economics here, more money, and with power to heat maybe around 50%. So both these 1 and 2 would clearly yield a positive economic benefit. Now there's other cases as well, which we have described in the paper, and I would be happy to share you with that information if you want. The third case, the final case with flexibility, is that where we do about the same analysis now as we did for a whole city, and now but we're going now to a single house, and doing a very detailed building simulation. So we have the building dynamics even there, and the interaction of the building and the energy system. And this building would be an all-electric building with photovoltaics, and we would apply a range of different flexibility measures, as you see here, with DSM battery, with thermal storage as well. And the main results would be here, again, that when linking the flexibility measures to the spot price of electricity, so we do an current optimization against the price of electricity, we could reach about 25% savings in the yearly electricity bill with these kind of schemes, which is quite a major achievement. Also, most of the electricity in a single house, most of that could be actually kept in the building. So we could decrease if you have just a PV system connected to the grid without any flexibility. Compared to that, we could decrease the feeding of electricity in the grid by almost 90%. So most of the electricity would remain definitely on site. Now, ladies and gentlemen, let me then just move to my final part. That was the technical part, and the final part is really on the market take-up, for which I would like to make a few remarks. And one of the reasons is that, of course, flexibility measures, flexibility technologies are new technologies, and we need to think about their market introduction as well. There's actual factors that affect the diffusion or penetration of innovations, and for instance, the communication channels which are linked to the decision making, but also the social system, the social context in which decisions are made. So those two things are definitely very important, and if you put this into a more sophisticated frame, which is the decision-making process linked to the adoption or diffusion of technologies, you see that the penetration of the new technology, what would that mean is always a positive decision to buy that technology or to take that technology on board. So there's always a decision behind diffusion or adoption of new technology. And you see then a range of factors here, let's say internal factors, which affect your decision. There's external factors like the social system, the norms of the society. And there's a lot of behavioral factors too, which will affect then the decision for making a positive purchase of the technology. And of course, innovation itself has also plays a role when people make a decision to buy a new technology. Now the whole process itself ends up in what is interesting for us is this, of course, the positive decision making of the technology, which leads then to a market share increase over time. And that can be described with different models, for instance, the classical diffusion model. And I use here as an epidemic model as an example to show how different technologies penetrate. You can mathematically describe this easily with a logistic function, which is also known as the sigmoid curve or S curve because of its shape. There is one parameter which is very important, the beta, which is the adoption rate. There's a huge literature on diffusion models and on penetration, but this model would be the basics. This would be the simple diffusion model, and I use it here just to give you some examples on the differences on the penetration of different technologies. And you see here in the next slide slightly how the S-curves look like and how the beta, the adoption rate, which is the key parameter, how that would affect the market take-up of a technology. This is now just a hypothetical example. The adoption rate, you see, the larger the adoption rate, the larger the speed of penetration, the steeper the S-curve will be, and the lower the beta value, you see that there will be even a lag in penetration. In this case, the adoption of technology, all the kind of factors which will affect that is lumped, embedded in this parameter beta. And you could envision that, for instance, financial support or price will affect this beta, and as well as changing behavior would improve the adoption rate itself. So much of the, let's say, social system and decision making is really linked to this single parameter. Next, I just give you finally a few examples from earlier studies about the penetration rates, where we use a lot of empirical data and fitted the empirical diffusion or epidemic diffusion model into that, and we get different values for the adoption rate. And in this table on the left-hand side, we list some of the adoption rates, penetration rates for different technologies. And we observe that technologies, typically on the end-use side, they would have higher adoption rate. And that was one kind of observation, that let's take technologies on the, let's say, corporate side or consumer side. So on the consumer side, end-use side, we would see much quicker take-up of the technology. Now we applied that also on the right-hand side to look on the policy cost of the, for different technologies to penetrate. And here again, we see the same kind of conclusions, is that technologies, and that's the lower boundary here, the technologies which are closer to the consumers, to the end use, the public spending that you need is much less. So you get much more for your money. So the policy cost shown here as euros per megawatt hour would be much less for the end-use technologies. We also saw a very interesting phenomenon, not shown in the figures directly here, is that the policy measures themselves have also an effect on the policy costs. So, for instance, if you just subsidize the product, as for instance the feed-in tariff would make, so linking your policy to product support, that would actually become more expensive than linking your policy, for instance, to the process which brings the new technology to the market. For instance, technology procurement. In case of Sweden, you see that the policy cost, that's the cost of the public spending vis-a-vis the impact that you get. We get much lower cost here. And we draw a conclusion that if you compare these kind of a proactive a kind of a catalytic process-bound measures vis-a-vis more kind of passive volume-based measures, these kind of catalytic ones may be a factor of 10 more efficient. Sometimes we saw even the cases a factor of 100 more effective than using these kind of more traditional kind of volume-based tools. So ladies and gentlemen, I think we are soon coming to an end of the presentation, and let me just wrap up my key findings, and I would like just to highlight maybe a few points. First of all, on the energy system flexibility, I think is that through this new kind of thinking in flexibility measures, we could significantly enhance flexibility so that we could incorporate large schemes of reliable renewable electricity. So large schemes of wind and solar, I think we can come around the question of energy storage in some way if we want, and here we can use demand-side management and power-to thermal as examples. This kind of power-to thermal measure seems to be very effective, and we get much flexibility from that. We get also from demand-side management that adds on that, but maybe in less in terms of percentage. A final maybe highlight is here is to say that those technologies close to the end users and consumers, there seems to be a potential to more quickly adopt those, and I think that may be a good news for flexibility measures as well as most of the flexibility measures would be closer to the end users in the silent energy. So, ladies and gentlemen, so I think that's what I had to say today, and I thank you very much for your attention, and I'm ready for any questions.